Okay, we're back for video part 3 of Unit 12, talking about solutions. We're going to continue in this video what we started in the very short last video, talking about different types of mixtures. Again, our focus is mostly going to be on solutions, but we'll touch on the other types of mixtures toward the end of this video as well. A few more characteristics of solutions. They have small particles. They're small enough to where they do not settle out. They're small enough to where they do not scatter light. They're small enough to where they are indistinguishable from the particles around them. They're transparent, meaning that light passes through them easily without being refracted or being blocked. They do not separate if they are left all by themselves. If you take salt and water, for instance, and stir it up, it will stay stirred up. It will stay mixed. The salt won't, after a while, settle to the top or to the bottom of your container. It will all stay separated out. Solutions, if you truly have a solution, you cannot filter out the different components of that solution using filter paper or some other kind of mechanical filtering process. You can't sift it out, okay? Because again, it's all existing in a single state of matter, and so if a little bit will pass through a filter, then all of it will pass through a filter. Solutions do not scatter light. That's a test. If you've got something that you're not sure if it's a solution or not, you can shine a very strong light through it, like a laser or even a strong beam flashlight. And if you can see the light passing through that container, if it leaves a trail, then it's scattering particles. And those particles would not be there if it's really a solution. That's something called the Tyndall effect, and it should come up again later in this video. Talking more about solutions, one class of solutions are what are called electrolytes. Electrolytes are any substances that when you dissolve them in water, they allow electricity to be conducted through it. You hear the word electrolyte often when you're talking about sports drinks like Gatorade or Powerade. In truth, an electrolyte is anything that has some kind of a charged ion that could conduct electricity. Pure water does not conduct electricity very well. Electrolytes are important if you're an athlete, because as you sweat, your body loses things like sodium and calcium and potassium, and replacing those are important so that your muscles and neurons can continue to do the job they're supposed to do. If you run out of them, then you can get fatigue, you can get muscle cramps, and so it is important to have plenty of electrolytes in your body. Substances may dissociate in a very small fashion. That would make them a weak electrolyte. Strong electrolytes, when you put them in water, they will completely break apart. Most ionic substances are strong electrolytes. Some polar covalent substances can be weak electrolytes. That should come up at another time. The dissociation of an electrolyte is when you have water molecules, which, remember, are polar molecules. They have a positive end and a negative end. They will surround an ionic solid, and then they will use their charges to sort of pull apart those different positive and negative ions from that substance. Okay, so for instance, what we're looking at here would be a typical ionic cube-shaped solid like sodium chloride. You have your chlorine atoms here, your sodium atoms here. Your water molecules, using those hydrogen bonds, which, remember, that's what makes water so unusual, is all of its hydrogen bonding, they would surround and pull apart those different ions and spread them out. Like I said a minute ago, most ionic compounds are electrolytes. Some polar covalent compounds are electrolytes. Not all of them, and they typically do tend to be weaker electrolytes than the ionic ones. Now, ionization is similar to dissociation. It's taking polar covalent molecules and breaking them up into what are called aqueous or aqueous ions. Okay. One example you see right here is you have nitric acid no, I'm sorry, that's not nitric acid. Yeah, that is. Nitric acid, HNO3. When it reacts with water, the water is going to pull the hydrogen ion off of that nitric acid molecule to form what's called hydronium ion, H3O, and then also nitrate ion, which would be just NO3 with a negative charge. A non-electrolyte is any substance that when you put it in water, it will not conduct electricity. Most nonpolar covalent substances are non-electrolytes, and again, that's simply because they don't tend to have charged regions on their molecules. They share their electrons very, very evenly, and so there's no charges really, nothing really for the water to pull apart, nothing that will ionize or dissociate in such a way to where electricity can pass through it. Now, some molecular substances, some nonpolar covalent substances will still dissolve, but there you see something called solvation. It's a little bit different from ionic dissociation. Water molecules, again, using their hydrogen bonds, will still be able to pull apart some of these solids. What we see right here is looks to be a solid of perhaps some glucose, some kind of a sugar. You can see these large sugar molecules here. The water is pulling apart these sugar molecules and surrounding them, which keeps those, which allows that sugar to dissolve. But you would find, for instance, that sugar is not going to make a good electrolyte because these molecules do not have strong polar charges. Okay, they tend to be nonpolar in nature. Larger molecular compounds, like I just said, don't break apart into ions. Here's sucrose. This is one of my favorite molecules because you've got a glucose molecule bonded to a fructose molecule, and I think it's awfully sweet. It looks like they're holding hands. Yeah, just random fact. But they don't break apart into ions, and so you've got a lot of sugar dissolved, say, in soda. The soda is going to be a good electrolyte, but it's not going to be because of that dissolved sugar. It's going to be because of other ionic substances that are broken down in there. I'm sure there's going to be some sodium ions. You're going to have phosphoric and carbonic acid. Both of those tend to be good electrolytes. But these molecular compounds, although they will dissociate, they will solvate, they'll dissolve, they will not be real good conductors of electricity. Now this is a typical setup showing, and I'm not sure how well you're going to be able to see each one, showing three different examples doing what's called a conductivity test. Over here what we have is we have sugar dissolved, we have a little ion bridge, and we have a battery and a light bulb. Two electrodes are running into that, and you can see here that the light bulb is not lit up. So the current is not making its way through here because the sugar water is not a good electrolyte. This right here we have acetic acid, which in other words is just vinegar. Vinegar is a pretty good electrolyte, and you can see here that there is some light coming from this light bulb right here. Fun fact, acetic acid or vinegar is present in a lot of foods. Pickles, for instance, are pickled, preserved in a vinegar solution, which is why a lot of athletes swear by drinking pickle juice to help get rid of cramps. And this last example right here, we have salt, good old sodium chloride, ionic solid. It's been dissolved in water, and we have a very, very bright light bulb here showing that out of all three of these, that ionic substance is your best electrolyte. On electrolyte, weak electrolyte, strong electrolyte. In the non-electrolyte, the solute remains as molecules. In the weaker electrolyte, you have some molecules and you have some ions. And then in a strong electrolyte, which dissociates completely, you only have those aqueous ions. So you have a lot more charged particles to conduct that electricity. Alright, now we're done talking about solutions. We're going to look at a couple heterogeneous mixtures. The first one we're going to take a look at are called suspensions. Suspensions typically have very large particles, usually large enough to where you can see them. They will definitely deflect light. Got some sizes on here. If it means anything to you, they are greater than 1,000 nanometers in diameter, I suppose. In suspensions, the ingredients do tend to settle out, whereas in a solution, like I said before, they stay suspended. In a true suspension, like muddy water or smoky air or milk or alphabet soup, if you leave them alone long enough, then the different ingredients, although they may be very well mixed, like in the case of milk, they will eventually settle out into different layers based on their density. Okay? They can be filtered out. You can, for instance, filter the fat out of milk to make low-fat milk. You can filter dirt out of dirty water. You can filter coffee grinds out of water that has been run through ground coffee and filter paper. In order to stay suspended, they have to stay agitated. You have to constantly stir them up. This is why when you buy paint, house paint for instance, you have to be sure and stir it, or else the mixture that you paint with is not going to be the same color that you bought at the store. It's also why they put them in big shakers and they shake them up real good to make sure that that's the color that you really want before they let you buy it. Some common suspensions that you run into. Your whole blood is a suspension. The liquid part, the matrix, is plasma. It's mostly salty water. You also have solids in there like platelets, red blood cells or erythrocytes, white blood cells, all the different kinds of leukocytes. Muddy water, I mentioned that a minute ago. Calamine lotion. If you know, you put calamine lotion on when you have a mosquito bite or poison ivy to help alleviate the itch. It says on that and other medications, be sure and shake it very well before you use it. That's to resuspend all of those settled out particles. Another kind of heterogeneous mixture are colloids. Colloids are somewhere between suspensions and solutions. Their particles aren't as large as the particles in the suspension, but they're also not as tiny as they are in solution. In a colloid, those particles are going to tend to be medium-sized, which, according to this, is going to be somewhere between 1 nanometer to 1,000 nanometers in diameter. They also cannot be filtered out. If you have a colloid and you run it through filter paper, the particles should be small enough to pass through with whatever they're dissolved in. They scatter light, though, because they exist in more than one phase at a time. You can shoot that beam of light through there and you get, I mentioned earlier, the Tyndall effect, which is one way that you can test the difference between a solution and a compound. Some examples of colloids: paints, Jello, for instance. If you take Jello and you shine a very strong light through it, you can see the path of that light beam. Milk, mayonnaise, whipped cream, shaving cream also, fog. If you have fog, you've got water particles which will stay dissolved in the air. Clouds, butter, and cheese are also colloids. If you have a piece of cheese, it's not going to settle out like whole milk would settle out. Those particles are small enough to stay suspended, but they are still in distinct different phases. That brings us to the end. Thank you for watching.